everyone. Tomer and I are super excited to be here at Data and AI Summit 2023. But before we start, you're all probably working with big data, so you'll most likely encounter this sort of error with regards to storage exception, or spikes in your Kafka leg, or simply an error message that means the data could not be queried. This is exactly the talk for you. Today, we're going to talk about taking your cloud vendor to the next level and how to solve complex challenges with Azure and Databricks. My name is Itai Yaffe. I'm a senior big data architect at Akamai, and with me today is Tomer Patel, who is an engineering manager at Akamai. You can reach both of us over Twitter and LinkedIn. What are we going to learn today? So first, we'll talk about the main challenges of a cloud-based massive scale data infrastructure. We'll talk about how to iteratively architect such an infrastructure to mitigate those challenges, and we'll give you some tips for optimizing such an infrastructure. A little bit about Akamai. So our motto is we power and protect life online, and the company was founded over 20 years ago with a goal to solve what was then the toughest challenge of the early days of the internet, and it was sometimes jokingly referred to as the World Wide Web. Today, Akamai has three main pillars. The first one is CDN, or Content Delivery Network, and the goal is to bring the content as close as possible to the consumers, which is each and every one of us. The second pillar is security, and the idea is to protect the data, the systems, and the digital experience of each and every one of us and the businesses worldwide. And the third and relatively new one is cloud computing, and the goal is to allow businesses to run their workload securely pretty much anywhere in the world. Just a little bit about Akamai numbers. So I think the biggest number here is 30% of the internet's daily traffic goes through Akamai servers. That's quite crazy. We have over 10,000 employees worldwide. And as of last year, Akamai processed about 50 exabytes of data using Databricks. Our focus today, as an example, will be WSA, or Web Security Analytics, which is a unified platform that enables our customers, Akamai's customers, to assess a wide range of security events, analyze them, and take informed actions in real time. As you can probably imagine, this is a massive scale data infrastructure. Generally speaking, it's about efficiently handling massive amounts of data at scale. And this sort of infrastructure comes with challenges. And the three main ones are processing the data, storing the data, and analyzing it. If we take those challenges and look at them in the context of WSA, the first one with regards to processing, we're talking about 10 to 14 gigabits per second, and that keeps increasing. Not sure if you can all see, but the graph here shows that in one event, one recent event, one of our customers had a spike of 33 gigabits per second. So those are huge numbers. And we also have a very strict SLA where we need to have the events that are intercepted by our edge servers being available for queries in our data lake within 5 minutes from the moment they happened. With regards to storing, we're talking about over 6 petabytes of data that we keep for 31 days. And with regards to analyzing, we're talking about hundreds of queries per minute, where 99% of those queries need to finish or return within 10 seconds. Each query can scan hundreds of terabytes, and there are over 60 dimensions, which means there's an almost infinite number of combinations, so we cannot pre-calculate the results. How you can architect and re-architect these infrastructure to mitigate those challenges. So that's a very high-level overview of the CSI architecture. CSI stands for Cloud Security Intelligence, which is the division that Tomer and I work for, and also the division where Web Security Analytics is one of the products that it creates. So from left to right, depending where you stand. So the events are being intercepted by our edge servers, the raw data. Then it passes on to our receiving layer, which I'll talk about in a minute. But generally speaking, those events are being stored, the raw data is being stored in Avro files in Azure Blob Store, and some metadata is stored in Kafka. And then at phase number 4, the data is being processed by Azure Databricks, and again, we'll dive into that
in a minute. And the data is stored in Delta Lake tables, so it can be queried by our proprietary UI, which you can see on the right-hand side. And customers can log into our control center, slice and dice through the data however they like, and then the query is being sent to Databricks and returned to the UI, and Tomer will elaborate on that later. Let's focus for a minute on the receiving layer on this part. And so, as I mentioned, in the receiving layer, essentially what we have is the raw data stored in Avro files. Why? Because Avro is write optimized, and we want, in this phase, to store the data as fast as possible. But we also store pointers to the files, or the names of the files, as Kafka messages. Why we do it like this, and not storing the raw data in Kafka as many organizations do? Two reasons. Cost, obviously, blob storage is cheaper, and also performance and scale. Now, in addition to storing the pointers to the files, we also store a little bit of metadata on each file, like the size of the file in bytes and the number of records, and we use that later on when we process the data. So we will talk a lot about storage today, and we actually use three types of storage in our pipeline. So the first one is the standard blob storage, which is relatively write performant and relatively cheap. In one case where we actually need the very minimal latency, we use what is called premium blob storage, which is much, much faster, but as you can guess, much more expensive, about 10x the price of standard storage. And finally, we also use what is called ADLS, or Azure Data Lake Storage Gen 2, which provides additional capabilities like the Hadoop-compatible access and hierarchical directory structure for those data lake-related workloads. Okay, now I'll hand it over to Tomer, and he'll take you through the WSA architecture.
Thank you, Itai. You hear me? No. Yeah, now you hear me. Great. So let's focus on the right end of the slides, inside on what we're doing in Databricks on Azure Databricks. So I want to show you the WSA architecture, the web security analytics architecture. We'll start from the left side on the ingestion, and then we'll go on the right side. So if we'll start from the left side, you'll see on what Itai just mentioned about the Kafka and the storage. This is from the left. Then we have basically ingestion workload, which is in Azure and is written in Spark. This job actually reads the Kafka message, then gets the path, and then reads those files from the storage account. Beside this, we have also compaction, which in Databricks it's optimize, and retention. We have a separate job for compaction, optimize, because if we'll do it in the ingestion time, it will affect the SLA, and we can't wait for it. So this is why it's in a separate job, and this is running. The optimize runs once an hour and goes on about the last 3 hours. Why? To get late delivery messages. And the retention runs once a day. These are those jobs. And of course, all these pipelines are working with a Delta table, which is mounted to a storage account. We'll work through about the table and the sizes and everything. And now I want to jump on the right side. So on the right side, basically what we propose to our customers is a UI, where the users, our customers, can drill down, can aggregate, can see whatever events they got, security events. And therefore, we use the backend proxy application, which gets those API calls from the UI and then split the calls in between of our applications, which we called it as query builders. Each query builders actually transforms or builds the query itself, the SQL, the Databricks SQL or Spark SQL, let's say. And each and every one of those query builders are working with separate DB SQLs, SQL warehouses. Why did we split it? Because we have different use cases and we wanted to leverage in between of all those use cases. So for example, we have a query builder slow that all the, let's say, queries that we know and we identify which are taking more time than others will go to this path. So it won't affect other other queries. And we also have a query builder specifically for big customers, because we know that the big customers which have a lot of data open a lot of tasks, and therefore we don't want them to interrupt with others. So we have a different DB SQL sizes between those. Now you can see that we have feed 1 and feed 2 where we're exposing 2 feeds. The first one is the second one is basically 1% out of the second one. And let's focus about the delta table. So the delta tables that we use are really huge. We're talking about 6 petabytes of data. So with this comes a lot of challenges, and we'll see in a moment. Beside this, as I said, we're using Delta Lake. So beside the Delta Lake, there are other formats beside Delta, if it's Apache UD and Iceberg. We get a lot of advantage of using the Delta formats. For example, the ACID transactions, and we use it a lot across all of our applications. Beside this, we can versionize the files. We can go back and we have a trailing, so it's really important if something was corrupted, we can back it up. And of course, it stores the transaction logs, which we can then identify it. Beside this, we get a really good advantage of the ecosystem that we get. We can use it for research, threat research, and data scientists. So it's really important. And beside this, we're using the storage, the Azure Data Lake Storage Gen 2, because of what Itai just mentioned earlier. I want to go about the storage limits. So I think most of you or some of you know that each storage has limits, no matter on which cloud we're using, if it's AWS, GCP, or Azure. And those are the metrics that we are seeing all the time, that we are this is putting us attention. If it's the ingress, egress, and the transactions per second. So I want to specify the problems that we suffered from or we identified during all the transition from our on-prem systems to Azure Databricks. So we received a lot of throttling and server busy errors. We're talking about hundreds. At average, we're talking about 300K, but in general, it can be even more. And of course, it has impacted all of our pipelines. It means the ingest, the query, the retention, the optimize. So we couldn't meet our SLA at all. So the first solution was going and talking with Azure and seeing how we can leverage all those issues on the storage. And Azure basically enabled us a preview version of the storage, which is called regional storage. Regional storage means that behind the scene, there are multiple clusters behind the scene of the storage. We don't see it, so as customers of Azure, we can't see whether it's one cluster or more, but it's behind the scene. And we got into this preview as requested. And you can see that from the input storage and the output storage, we have multiple clusters. So from the left side, you can see that we have on the inputs between 6 to 7 and the output between 9 to 10. And as you can see, all the metrics of what were increased in order to support our massive scale. We couldn't work without this. Basically, the query side, everything was impacted and we couldn't meet our SLA goals. And this is a huge milestone that we got an advantage of. Beside this, Azure told us, okay, guys, you're taking to a breakpoint, but that we can't really support you anymore because this is really large. So you need to re-architect the data. So therefore, we went into a process of re-architecting and maybe talking about sharding. So let's go back for the other, the previous architecture that we had. So this is architecture, if you remember. And what we did is basically splitting the pipelines. We basically split those pipelines into 6. So on the left side, you can see the sharding app, that this is what we created. It's like an app in the middle, which separates the data into multiple pipelines. The separation is basically by the customer ID. And we had a trade-off between separating from 1 into, let's say, 20 because of performance, that we don't want that it will interrupt on the other side, and it will cost us more money. So basically we separated, we did some testing, evaluation, and we separated it into 6 different pipelines. So you can see that for each pipeline, we basically added all those things that we have. If it's ingest, optimize, that is compaction, retention, and of course, each one of them adds separate storages, and now I can leverage the egress, and transactions per second. Beside this, each and every one of them, of course, add a different table, which is mounted to a different storage. And on the query builder, we basically built in the same mechanism that we splitted the data. We also build the query upon the specific table. I want to go to the next topic. So we had a lot of advocations of get status errors, of APIs, not errors. And it impacted us a lot in our ingest, in our query, and we had a lot of issues with that. And therefore, we had a lot of talks with Azure, with Databricks, in order to solve this issue, why we have so many invocations of this API. So you can see that from the query side on the right, this is our performance. For the different colors are different API calls. You can see that we had blips every once and then, and it interrupted the SLA for our customers. On the left side, you can see that the number of advocations of the get path status errors. So what we did, we had a lot of investigation together with all the teams, including Databricks, Azure, and us. And basically what was happening is that in the DBR version, they used different API calls or API calls that are redundant already in Azure. And therefore, what we had to do is, after the fix, just to update the DBR version. So I would recommend you to all the time keep tracking on the DBR versions and just be ahead of schedule with that, because this is really important. There are a lot of bug fixes, and this really helped us. I want to go specifically and focus on the query SLA. And in this area, we had a couple things as well. We have a couple of facts on WSA. First of all, the data that we're showing to our customers are raw data, the attacks themselves. And on the other end, we also aggregate the data between hours or minutes even till 31 days. So we have all the variety of queries, and we can't really have a straight solution that can be the best for everything. So our queries are taking more than tenths of a second, and we can, if a customer, if each and every one of you are going to a website and it takes more than, let's say, 3 seconds, 7 seconds, 10 seconds, it's crazy, and we won't wait for that, right? So this is what happened for us when moving into Databricks at start. And we have a couple of recommendations that we feel that we should share with you guys on what has improved us. So we talked about the regional storage and the sharding and how it allowed us to perform better. But basically, there are other things that we added in order to support it. So we used Databricks Photon. It improved us really amazing in regards of the query and in regards of on the ingest side. It does cost double, but we couldn't basically work with WSA, with a product, without Photon. And this we'll talk about it tomorrow in tomorrow's session. We're doing another session tomorrow. And the next topic is that we also developed an in-house load balancer on the SQL warehouses. Previously, we worked on all-purpose clusters, and then we migrated to DB SQLs. This also will be shown tomorrow in the session. And the last topic that we recommend on the SQL is sampling. So what we started to do, and I'll show you right now, is sampling. What is sampling? So why we want sampling? So sampling is we can guarantee better response time because it's less data. We're not talking about 6 petabytes of data. The second thing is that it's cost reduction because it means that if I'm querying on less data, I don't need all those resources on SQL. And the last thing, it reduces all the issues that we've observed before that. So what we did is we created a POC of sampling data sets of 1%, 5%, 10%. It doesn't matter exactly which percent. And we built sort of a decision tree on whether to query in the sample data or not to query in the sample data. So we have a strict, for example, specific APIs, specific accounts, and not. By default, of course, it will be on. And for specific use cases, we will move the query itself to non-sampling data. But for customers, probably it doesn't matter if they have accuracy of like 2% off. So it makes them still confident with what they see. And we get a guarantee of less cost and better performance. So they get their responses better. And the next move that we want to go on is building the decision tree as a ML model on top of it, and will make the life easier. So what we have seen. So we're talking about 6 petabytes of data, right? Big customers, small customers. Our query performance is truly amazing. We can say that like 88% of our queries, or 85, let's say, in average, are less than 7 seconds. We're talking about huge amount of data. This is aggregated data, raw data, between minutes into 31 days. I want to deep dive into 2 more things for optimizing the massive scale data infra. So we'll talk about the data retention and compression formats. So how do we delete old records? So deleting the data older than defined threshold is something that everyone are doing, right? We don't want to keep all the data forever. It's costs a lot of money. But Delta Lake does not support what we see here to drop a specific partition. Instead, it provides a delete from. So as you can see from the query here. What we can see is that there is a potential impact on the deletion itself. You can see that on the bold, the bold there, you can see that number of added files are 3. So it means that when I'm deleting, it also creates new files. And this is something really bad for us, in regards of performance. So why does it happen? So Parquet files are immutable, and basically this is a huge problem. So what we did to avoid this issue is basically we created event by day, and we rewrited the SQL itself, so you can see what we did. Sorry. This is the previous one. This is the new one. And now afterwards, you can see that the number of added files now are 0. So we didn't add new files. What is the impact of it? So first of all, our partition is by customer ID and date. And the deletion, if you remember, that I recalled is that once a day. So we went from 4 to even 6 hours into 20 minutes. And this is amazing because it's less resources that we're working on. It helped us a lot. And of course, from hundreds of dollars per day, we reduce it to tens of dollars per day. And this is truly amazing. And of course, when we have less IOPS because we don't create new files, we basically just delete. The next topic that I want to talk about is the compression formats. I think it's an hot topic recently that everyone are discussing. So as you know, that the product WSA is working with Delta Lake tables and writes a lot of terabytes all the time per second. And Snap is the default compression format for Parquet files written in Spark. And of course, there are other formats that are supported. So LZ4, Z standard, gzip, and maybe we should test him, right? So the main goal is to reduce the amount of data written to read from ADLS, reduce the IOPS and the cost. And before that, we got a good recommendation on checking this up, thanks to Amir, which is sitting there. And we wanted to check as well the same issue also in our architecture. So the main goal, of course, was to reduce the IOPS. And we went with Z standard. Before that, there are other compression, gzip, LZ4, but for example, LZ4 wasn't ready with the Photon, and we use Photon. There was a bug. And this is why we went with the Z standard. So Z standard format was developed by Meta, and it has 22 different levels. The default is level 3, and Databricks supports the Photon, so we get a great advantage out of it. And it's super easy to configure it, so you can even take a picture. Really, really easy. Let me know when I can move on. Okay. Great. And we can also configure the level itself. So you can see also how we can configure. Yeah, of course, it's super important for everyone to basically to have it in all the ingested pipeline. If it's compaction, deletion, and ingest, otherwise you won't see the whole benefit out of it. So we did a sort of POC. We took 3 different levels. Of course, this is specifically for our use case. For your use case, if you have time, you have the money, you have the resources, you can check all the levels at the same time, but we just did 3 out of the 22. And these are the benchmarks that we got. So of course, there is a trade-off between performance and cost reduction. And this is something that you should take, obviously, in your schema, in your architecture and everything. So we took the level 3, the default one. You can see how much it reduced our storage, and this is truly amazing. And the last thing that I want to talk about is about Linode. So Akamai just announced that the new offering of a new cloud provider. It's called Akamai Connected Cloud, or previously Linode. And we're trying to optimize our workload and even do some cost reduction, work on Linode some of the things. We of course are trying to take into the advantage all the things that you've seen right here on the things that improved us and we benefit from in regards of performance and cost. And this is what we're applying as well in the migration of some of the stuff that we're doing. So I'll hand over to Itai.
Thanks. Yeah, mic is on?
No.
No? Yeah? Okay. Can you hear me at the back?
Yes.
Right, we'll just summarize and then I hope we'll have a few minutes for questions. So, just to summarize, we spoke about the 3 main challenges. So with regards to processing, we showed you a few ways to optimize your system. So for example, using Kafka to store only the pointers to the raw data. We also showed you the sharding methodology, which is a way to split your ingest pipelines to overcome storage limitations, for example. And obviously, you should avoid excessive storage invocations, as we've shown you, and upgrade to DBR versions. Upgrade to newer, DBR versions. With regards to storing the data, so there are a few items here. Anything from choosing the right storage type, blob store, premium, standard, ADLS. I couldn't recommend more. Please use an open table format. If you're using Databricks, Delta is the obvious choice, but please use something. Don't leave your data lake as a data swamp. And also properly delete all data. As you've seen, if you don't take into account the right way to use the delete from in Delta Lake, it might produce new files, which obviously is not something you usually want. And choosing the right compression format for your needs can also have great benefits. And finally, with regards to analyzing, Thomas showed an example of how sampling can improve query performance with relatively little impact on accuracy. Just before we wrap things up, a few things we care about. So Women in Big Data is a worldwide program that aims to inspire, connect, grow, and champion the success of women in all data domains. There are over 50 chapters worldwide, and everyone can join regardless of gender. So we encourage you to find a chapter near you. And there's also Women in Data and AI panel and lunch on Thursday, 11:30 a.m. Akamai has 3 more talks tomorrow. The first one is from Snowflake to Enterprise Apache Spark by Nick and Amir from our Asgard team. And thanks for the Z-Standard tip. Tomer and I will be in this exact room at 1:30 p.m. and we'll give you the sort of second half or the analytics aspect of our architecture. And finally, at 2:30 p.m., Yaniv Kuna, one of our colleagues, will talk about how we migrated from on-prem systems to the cloud. That's it for us. We really appreciate your participation, and we'll be taking questions now. Feel free to reach out for feedback over Twitter, LinkedIn, again, whatever you want. Thanks, everyone.
Do you guys run on a GPU or like CPU, all your ingestion?
What, sorry?
Do you guys run on a GPU servers?
No.
Or
No.
Did you guys try with the GPU?
No plans for GPU at the moment.
Not, yeah.
Okay. Okay. I'm curious how the Spark works in GPU. Do you guys see any performance implications of the GPU?
It costs more money, so...
But you can reduce the time, right?
it's a trade-off that we didn't still yet
Good question,
use
but
it.
we didn't try that.
You didn't try? Okay. I heard like now they naturally integrate into GPUs, like Apache Spark supports GPU processing.
The question is, does it support with Photon? Because when using Photon, not all the VMs are supported with Photon. So
Okay.
this is why we had specifically VMs that we used in our...
Okay. Okay. It's done.
No, that's okay.
Thank you. I heard like Photon is coming to GPU, so they are working on it. So.
Oh, okay.
Cool. Thanks.
Thanks.
There's a question in the back. A few questions, actually.
Hi, can you go back to the slides 47, please? Thank you.
To which one? Ah,
Slides 47.
to-
So there, where you show the different query builder.
Oh,
Query builder?
Yeah,
ככה.
yeah, 47.
This
Yeah,
one?
Yeah, this one is good enough. So, what do you mean by that? So the query builder is different service linking to the different.
so the query builder
warehouse?
actually is a Spring Boot application, Java,
Okay.
that opens a JDBC connection into those DB SQLs. And what we do is basically there is all the logic to build the SQL itself.
So,
So-
the way it works, it gets a request from the UI, and it sort of works as a middleware, as a translator from the UI request into SQL.
So you sort of like direct the traffic into dedicated SQL data warehouse. So that's the thinking.
What, sorry? I didn't.
Oh, it's okay.
No,
I
that's
think
okay.
I got the idea.
Okay.
Thank you.
Sorry.
Hi, this is Venkat. If you don't mind, can you go to the deletion slide?
Deletion side?
Yeah. So the solution you guys tried, like the next one.
Yeah. One more? Another one.
Yeah. So is this you guys tried your own logic? Like you guys, is it before the deletion vector feature that came into the Delta Lake, or even you guys, the deletion vector didn't help that much?
So if you use the describe history command of Delta Lake, you can see the metrics. And then when we found out it actually creates new files, then we started investigating, right? It creates new files because we didn't delete on a whole day basis. So we deleted only some rows inside the partition. That's why it had to create new files.
No, but if you would have used a deletion vector, the new feature that in a Delta Lake.
Again.
That's what I was asking. Is it before that? Okay.
You're right. So the question was about deletion vectors. So when we did that, deletion vectors were not available yet. But yeah, that's a good question. So deletion vectors might be a good idea to try as well.
So, but still after deleting, like you didn't create any zero rows, but when you do a vacuum, it goes and create new files and everything because it
No,
organizes.
once you vacuum with the new deletion, like with not with the one that actually creates new files, but the one that doesn't create and deletes the entire partition effectively, then the vacuum is like that. Tomer showed the metrics. It was very surprising in the first few days when we saw it. We said, okay, how come it only takes a few minutes? We thought that something was wrong, right? Because
So the number you're showing, like 4 to 5 hours to 20 minutes, is that your vacuum time?
that was what,
Yes.
before
Okay.
with the not correct deletion statement, and afterwards with the
Okay.
let's say optimized.
Okay.
deletion.
So my another second question, like the compression, right? Like so you guys, like if you go back to the slide. So you guys got only performance of
Compression?
reducing the storage, but it didn't boost any of your query performance. Like your I/O didn't change.
Yeah. So the question was, did we consider like other formats with regards to? Did we look only to reduce the storage or improve performance as well? So I think that, as we've shown, both cost and storage were like very significant items for us.
I think for everyone in the industry, basically,
everyone
so
agree.
it's
And so that was the focus because the query performance at that point was already quite good, as Tomer showed. So the focus was more, okay, how can we reduce the cost? How can we, avoid as much as possible or minimize the storage issues?
So no, I think I got like the storage, like the main focus to reduce the cost on the storage. But like, do you guys seen any performance improvements with any other compression formats?
on the storage itself. So you mean
Like from I/O perspective, your query perspective, like a read and write. Okay, you changed my format, and now my write spiked.
The best person to answer that question sits right there, Sharon. Thanks. She's from our performance team. But generally speaking, it wasn't that significant. I mean, there was maybe
Slightly,
sometimes it was a bit better, maybe a little bit worse, but it wasn't statistically significant.
But of course, from the storage impact, we had less issues on the egress, on the storage.
Right.
Because
So you guys are just Azure shop, like you guys tried this on a AWS or something, the compression format?
No.
No. Okay. Thanks.
Okay. Okay. Cool.
My question is basically, you did the re-architecture of your pipelines, and then you tried out different solutions for your SLMSs, like compression, data deletion, and things like that, right? Like, so in some places I've seen cost reduction, but in some places I've seen cost up because of the grade that you're picking or like the format that you're picking, right? So overall, when you were done with all of your re-architecture and then when you were meeting your SLAs, how did the cost and performance, obviously that was actually one of my questions too, but I think you answered that. How did that impact overall? Like, I'm looking at the big picture after the solution was redesigned.
So I don't want to sell all our secrets. Tomorrow, 1:30 p.m., we'll be here. We'll talk about cost and performance. But a sneak peek, both of those items were the focus of the entire work the group has done over the past 2 years with Databricks and Azure. So I think that, generally speaking, we improved performance and reduced cost, but there's always a trade-off. And yeah, let's just talk about it tomorrow.
And of course, just one more note: when you come to the 100%, everything is migrated to Databricks, everything is okay, and we meet the SLA. Now is the time to talk about cost, and then we reduced. So this is what we did.
Hi guys, just a very quick question. Is it possible to get a copy of the deck? Can we get a copy of the presentation?
I think so, right?
I think so, but
we can
we'll
send
have to
you.
ask the organizers.
Yeah.
But if not, we'll probably
We can
just
send
upload
you.
it
Yeah,
ourselves,
no problem.
All right, thank you.
Nice. I think we'll take questions offline because I'm guessing there's another.
We have about 2 more minutes, so if there are any last minute questions anybody has.
Okay, there was a question here, actually. I thought we were out of time, but if we do, so. Here, right here, yeah, the question. Yeah.
Where you use the Kafka queue as the pointers, is there a reason you didn't use autoloader and the storage queues for that?
Go for it.
Yeah, that's a great question. So the main reason, and again, that's the work the team has done. I wasn't part of that part, but autoloader at that point just wasn't scalable enough for our purposes. Even just the file names. I'm not talking about the raw data, which is huge. Even the file names, we are talking about huge number of messages. And so it's. But I do think maybe today it has improved enough for the.
So you'd exceeded the scale of autoloader at that time, so you solved it that way. Fair.
All right, we're up on time, but Tamir, Itai, thank you so much for coming.
Thank you, everyone.